we're back at AP Review. This is 2005 Form B, AB, BC Free Response 4. We're given a graph of F that looks like this. The points that I drew on here are labeled. So -4, -3 is labeled, -1, -2 is labeled, 1, 0, or 1, 2 is labeled. So 0, 0 is not, but it's very clear that the line goes through the origin. 2, 0 is labeled, and 3, -2 is labeled. I'm just lazy. So here's F, and they give us that g of x is defined as the integral from -4 to x of f of t dt. So time out before you do anything. Looking at this graph, you see that you could easily find the area under these curves using basic geometric shapes like trapezoids and triangles, like the accurate area, not an estimation. You can also see that because these parts of the graph are lines, you could be asked to find the derivative of this graph, f prime, by finding the slope of this graph. So the reason I mention that is what's going to happen here is you're going to be asked to do stuff with g that involves finding the area under this graph because g is the integral of this graph. You're going to be asked to do stuff with g prime, which is just essentially this graph, and with g double prime, which is the slope of this graph. And all of those things are really accessible. The reason I mention it now is that when you see a graph like this as the start of a problem, you know those are the things you're going to have to do. And if you don't know that now, you want to know that moving forward because it's good to have an idea of what's expected of you. So let's start with part A. Let g be this function. For each g of -1, g prime of -1, and g double prime of -1, find the value or state that it doesn't exist. Okay, so first thing we should do here is find the relationship between g and the graph, right? So if I want to derive g prime, like if I want to derive g and get g prime, when you derive an integral, right, the second fundamental theorem of calculus says that if you derive an integral, what happens, and let me just give myself a little bit of room, g prime of x is going to be the derivative with respect to x of the integral from -4 to x of f of t dt. What happens when you derive and integrate is these cancel, and then you plug in the bounds and then debound, minus the lower bound de-lower bound. But what's going to happen is I just get f of x times the derivative of x, which is 1, minus a bunch of 0, because the derivative of that -4 is going to be 0. So the important relationship that I need is that g prime of x is f of x. This is the graph of g prime. Like, this is the graph that we're given. And then if I derive again, g double prime of x is going to be f prime of x, which if you wanted to put that into words is the slope of the given graph, right? So this is the y values on the given graph, right? G prime are the y values on the given graph, and g double prime is f prime, which is the slope of the given graph, right? So now when we're asked to go ahead and do stuff with that, so let's go ahead and find, knowing that relationship, right, let's go ahead and find some values. So I'm going to erase this stuff because it seems less important. Okay, so let's go ahead and find g of 1. -1. So g of -1 is the integral from -4 to -1 of f of t dt. So here's -4, here's -1. That's a trapezoid that should net negative, right, because it's below the axis. So it's a trapezoid that has one base of height 3 and one base of height 2, and has a height, or a base of length 2, if that makes you feel better, and a height of 3. So this is a negative because it's below the axis, right? 1/2 the height times the sum of the bases, right? So that's a 5 times 3, which is 15, so I get -15 halves, right? So that's my g of -1. Now, we saw already that the relationship, and it's worth noting this and then like keeping it sort of in your like list of info that you know, is that g prime is the same as f, which is the given y values, right? And g double prime is f prime, which is the slope of the given graph. So I'm just going to keep that up there so that I have it in my like information if I need it, and I'm going to erase down here so I can go ahead and actually find those values at -1. So g prime of -1 is literally the same as f of -1. So I go to the f graph, I look at what f of -1 is, and it's a -2. Great. Okay. G double prime of -1 should be the slope of this graph at -1, but what I want you to notice is that, so g prime, which is the f graph, is not differentiable at -1 because it has a little pointy thing, right? So, so g double prime is f prime, right? And it does not exist. Or you can say dne, right? If you like dne better, that's an acceptable math notation. Because f prime of x is not differentiable at x equals -1. It has a point, right? Like points and cusps make something not differentiable. So those are my first 3 answers. They were worth exactly 1 point each, right? Cool. Next bit. For the function g, defined in parts A, find the x-coordinate of each point of inflection on the open interval and explain your reasoning. Okay, so this is one of those times that we want to make a flow chart, right? So I'm going to do a terrible job of erasing around this, but you get the gist. Okay, cool, close enough. All right, great, okay. So in part B, we're asked for points of inflection of g, right? So that's what the ask is. We then want to make the flowchart to what the actual definition of this is, right? That's that g double prime equals 0 or doesn't exist, and this is the big thing, changes sign, right? Changes sign. But we already know from the information that we figured out in part A that the relationship between g double prime, or g and f rather, to talk about g double prime, is that g double prime is the same as f prime. So what this is saying, right, so in this specific problem, so problem specific, this is saying that f prime, which is the slope of f, does not exist or is 0, and changes sign, right? So that's what I need to find, the spots where the slope of this graph are either does not exist or 0, and we can find those pretty quickly. So the spots where this thing's slope does not exist or 0 are here, here, and that's it, right? And then we also have ends, right? So we have to consider the ends. Ends aren't points of inflection, but we should consider them on the chart. There are no places where this graph has a horizontal tangent, so there are no places that are 0, but there are 2 places that the derivative doesn't exist. So g double prime does not exist at x equals -1, which we already saw in the first part of the problem, and x equals 1, right? Those are the 2 places where g double prime doesn't exist. Okay, but in order to be a point of inflection, we need g double prime to change signs. Well, this graph has a positive slope here, right? The graph is increasing, and then it continues to have a positive slope here. So x equals -1 is not a point of inflection because g double prime goes from positive to positive, which is not changing sign, right? But after 1, the graph now has a negative slope, so the only point of inflection is at x equals 1 because g double prime, which is the slope of the f graph, changes from positive to negative. Another way to say that is that f changes from increasing to decreasing, right? Either of those would be fine. Again, what you want to try and make clear is that the slope, right, the slope of the given graph changes from positive to negative, or the given graph changes from increasing to decreasing. So the only point of inflection is at x equals 1. Cool. Part C. Let h be a different function. Oh, good times. Let me erase. All right, so the rest of the problem talks about h, not g, so we will erase our g stuff, right? And we'll try and clean this up a little, probably failing. Cool, okay. So part C, h of x is the integral from x to 3 of f of t dt. Cool, clever. All right, find all values of x in the closed interval for which h equals 0. Okay, so what this is saying, right, is this is saying that you're integrating. So let me kind of do a slightly better job of drawing this again. We'll see how well that goes. Okay, cool. Close enough. Okay, so that's supposed to go down to -4. Great, okay, cool. So here's the idea. Here's 3, right? So this is an area, right? This is an area, and you're integrating backwards. But in order for h to equal 0, right, when you integrate backwards, essentially, in order for h to be 0, the area has to net 0. So what they're asking in part C is, when does the area net 0, right? Meaning the same amount below as above. So if I integrate backwards, this is actually going to be positive because I'm integrating backwards, right? But then right here, this is the exact same triangle, and it will be negative. So the first place where h of, that would be 1, is 0. And the reason it's 0 is because this triangle above is a negative, and this triangle below is the exact same triangle, and it's positive, so it nets 0, right? The next spot, right? So that's the first bit. We know it's 0 there. Well, then here to here, is another spot where these two shapes are the same, right? So here and here, these two shapes are the same, right? So the second spot, h of -1, will also net 0 because essentially you already netted 0 here, right? You had the positive value that was down here and then a negative value above because we're integrating backwards. And then this negative value above matched with this positive value below. Oh, look, it nets 0. They're the same shape. The third one is the one that, ironically, I think if anybody's going to miss one, they might miss this one. The third one is that whenever you integrate from one bound to the exact same number, the area is 0. So the third one is that h of 3 is 0 because essentially you're integrating no width, right? What that would mean is no width. And that's actually one of the rules that we learn in calc is that if you integrate from a to a of some function, it's 0, right? Because the bounds are the same, you have no width, thus you have no area. So there are 3 x values. The 3 x values are 1, -1, and a 3 in whatever order you wanted to write them. So your part C is a 1, a -1, and a 3 in whatever order you came up with that. Cool. Part D. For the function h defined in C, which we just used, find all intervals on which h is decreasing. Explain your reasoning. Okay, cool. So again, my poor graph is totally a mess, but hopefully you'll manage. So part D. So we need to take what they ask, right? They asked when is h of x decreasing. We need to translate that into the definition of decreasing. So by definition, h is decreasing if h prime of x is less than 0, right? Cool. Well, now we need to use what we know about h. So since h of x is the integral from x to 3 of f of t dt, when we derive, and this is a little bit tricky, we don't get f of x. Because if you were to derive this, it would cancel out the integral and you would plug in f of 3 d3, which would be 0, minus f of x dx, which is a 1. So your h prime of x, right? So in this problem-specific translation, right, problem-specific, your h prime of x is equal to negative f of x. So what you're actually asking is for negative f of x to be less than 0, which is the same as saying when is f of x greater than 0. Once you know that's what you're looking for, now you can connect the dots with your eyes. So with your eyes, you want to say when is the given graph above the x-axis, right? Because that's the connection we need. So we need when is f of x greater than 0, and the only time when this graph is above the x-axis is from here to here, right? So the answer is going to be 0 to 2, right? Now, the AP includes the 0 and 2. I have a point of disagreement with them because I would argue that the graph is actually not increasing or decreasing at the values where f prime or where f is 0. But so the AP's answer includes them. I don't include them. You can take your argument up with the AP because I disagree. So cool.